This is your second lesson on probability. We're going to tackle some of the more difficult problems now. You will solve more complex probability problems. You will recognize and solve probability problems with mutually exclusive and independent events. Let's start off with this one here. A class is given a list of 20 study problems from which 10 will be part of the next exam. If a given student knows how to solve 17 of the problems, find the probability that the student will be able to correctly answer all 10 questions on the exam. Okay, what I'd like for you to do right now is pause this, try and come up with an answer, and then we'll discuss it. Alright, let's talk about this now. We have 20 problems, and the student starts studying them, and he studies 17 out of the 20, and then he runs out of time, so he has to stop studying. So he knows the first 17 really well, and the last 3 he just doesn't know at all. So we want to find the probability that he gets them all correct. So you need to think of this probability problem in parts, and a lot of the more complex one, if you think about them in parts, it might help. So first thing is, the test is going to be made up of 10 questions, and out of a list of 20. So how many, okay, we're going to do the probability in a second, but how many questions is that? Well, it's going to be 20 combination of 10. We're going to choose 10 out of 20, and the order doesn't matter. So this is your sample space. So this is your total number of ways that the questions can be chosen. Now let's look at the other part here. If a student knows 17 of the problems, find the probability that he's going to get them all right. So how many ways are there to choose the 10 from the 17? Well, you're going to, the student wants me to choose all 10 from the 17 that he studied. So that will be 17 choose 10, right? If all 10 problems were chosen from the 17 that he studied, then he would get them all right. So this is how we're going to set this up. So the probability that all of the ones that he studied will be from the sample would be 19,000 over 184,000, which reduces to 2/19. Let's look at this problem in a slightly different way. Kind of the same setup, but we want to know the probability that the student will be able to answer correctly exactly 8 questions on the exam. Kind of the same as before. The last question asked, what is the probability that he will answer exactly 10 of them correctly? Now I want to know what's the probability that he will answer 8 of them correctly. So we start the problem kind of the same way. Okay, choose 10 from the 20, and then this is a little tricky part here. How do we count exactly 8? So we want to choose 8 out of the 17, and then we're going to choose 2 from the 3 that he doesn't know. This way we're going to get exactly 8 problems that he will get correctly, and he's going to get exactly 2 of them wrong and get 8 of them correct. So you get this probability here, 72,000 over 184,000, which reduces to 15 over 38. All right, let's look at it one more time, see if you can figure this out. We're going to find the probability that the student will get at least 9 questions. Okay, this is not exactly 8, this is at least 9. All right, we're going to consider at least 9. That means he could get 9 right, or he could get 10 right. Now, when we have these at least problems or the or problems, you're going to have to do both of these probabilities and use the or, which means add them together. Well, we already did this part. The first time we looked at this problem, we found out how we can get them all right, all 10. Now we have to add to that the probability that he's going to get 9 right. So we're going to do the same thing here. We're going to go the probability of getting 9 out of the 17 correct, and we're going to make sure he gets 1 wrong. So we're going to choose 1 out of the one he doesn't know. This is my exactly 9, or exactly 10. So exactly 9, exactly 10. And the or means we're going to add them together. And that's going to give me half. If this question has said at least 8, then you would find exactly 8, exactly 9, exactly 10, and you add those together, and that will give you at least 8. So if I said at least 2, then you would have to do exactly 2, exactly 3, exactly 4, exactly 5, exactly 6, exactly 7, exactly 8, exactly 9, and exactly 10, and add all those together. Okay. Let's learn some new terms here. Mutually exclusive and independent. I used to teach both of these separately, but I find that trying to get students to know the differences between them was more difficult than learning them separately. So I'm going to teach them together so you can contrast them, compare and contrast these two concepts, so you won't get them mixed up. Mutually exclusive means that the events cannot happen at the same time. Okay, 2 probabilities that cannot happen at the same time. Like, what's the probability that you will go to Paris for your summer vacation, or the probability that you can go to Japan for your summer vacation? You could have two different probabilities, but you can't go to Japan and France at the same time. So that means they're mutually exclusive unless you take 2 separate trips. If you take 1 trip, you could not go to those 2 places at the same time, so they're mutually exclusive. Independent events are events that have nothing to do with each other. Okay, if one happens, it doesn't change the probability of the other. It's like, what is the probability that you're going to have chicken for lunch, and the probability that you're going to get A on your math test? All right, these two don't have anything to do with each other, so they are independent events, where one does not change the outcome of the other. Okay, so let's look at some of these. Mutually exclusive. Events are mutually exclusive if they cannot happen at the same time. Let's say the probability of Lisa getting an A in physics and the probability of Lisa getting a B in physics. She may have a 50% chance of getting an A and 40% chance of getting a B, but there's no chance that she can get A, B at the same time. So these are mutually exclusive. And in a Venn diagram, these two areas would not overlap because they don't have anything in common. You can't have the AB cross each other. All right. Okay. Now, what about two events that are not mutually exclusive, or what we call mutually inclusive? The probability of drawing a card from a deck and it being a 5, and drawing a card out of a standard deck and it being a heart. Well, there is a 5 of hearts, so these are not mutually exclusive, or they are mutually inclusive. Because if you count the number of 5s and count the number of hearts, I didn't draw all 13 hearts, but I did do all the 5s. But there's a 5 of hearts, and they are not mutually exclusive. The 5 of hearts is not mutually exclusive. It can belong to this group, and it can also belong to that group. So to find the probability of a mutually exclusive event, you have to subtract off whatever they have in common. Because if we count the 5s, we're going to have 4 5s, and we're going to have 13 hearts. But if we're counting 5 of hearts, then you're going to count the 5 as a heart, and you can count the 5 as a 5, so you count it twice. That means you have to subtract off one of those. So probability of event A, which are the 5s, there's 4 5s in the deck, 4 out of 52. And there are 13 hearts, 13 out of 52. You can't just add these because you'll have added this one card twice and get 17. Instead, you have to subtract off one of them and get 16 out of 52, which is 4 out of 13. Okay. What about if you want to know what's the probability of drawing a 5 or a 6? Well, drawing a 5 and a 6 are mutually exclusive, so you can just add them together. Since they have nothing in common, you don't have to worry about this part where they overlap. One card is selected from a deck of 52 cards. What is the probability that a card is either a heart or a face card? Face card is one with a king, queen, or a jack, and then a heart. So these are not mutually exclusive because you do have cards that are face cards and they are hearts at the same time. So you're going to do the hearts. There are 13 hearts in the deck. There are 12 face cards. We have 4 kings, 4 queens, and 4 jacks, so that's 12. You have to subtract off 3 cards, the king of hearts, the queen of hearts, and the jack of hearts, because you counted them as a heart, and you also counted them as a face card. So you subtract that, so you get 22 out of 52, which is 11 out of 26. Talk about independent events. Independent events are independent if one has nothing to do with the other. The probability that it's going to rain tomorrow is 20%. The probability if you flip the quarter tomorrow is 50%. So if you want to find out if it's what's the probability it's going to rain tomorrow and you're going to flip a coin and it's going to end up to be 50%, you're going to have to multiply these, because this is an and means multiply, or means add. So it's 0.2 or 20% times 50%. That means it's 10% chance that tomorrow you flip a coin, it's going to come up heads, and it also rains. Okay, make sure you always answer the question being asked. If they ask how many ways, how many, then it better be a counting number. It better not be a fraction. It can be 0, 1, 2, 3, 4, 5, and so on. It can be up to 650 million, but these are all how many. Probabilities are always some kind of fraction answer, either as a percent, either 1 out of 2, or 50%, or 0.5, and all these numbers has to be less than 1. You can't have a probability that's over 100%, or 1. Okay, it's either a 5 out of 6 probability, 2 out of 19, but not 11 out of 2. That would not make sense as a probability. Okay, so make sure that you answer the question being asked. They ask for how many, give it a counting number. They ask for a probability, give it a fraction. A quick hint, there's one question on the Google form that kind of asks this indirectly, but make sure you answer the question being asked. Poker hand. Let me go over this kind of important concept. Not the poker hand's an important concept, but figuring out the probability is important. So, what is the probability of getting 4 of a kind? 4 of a kind means a standard poker hand of 5 cards that 4 of them are going to be the same thing, like 4 aces, 4 kings, 4 twos, 4 eights. So to find the number of ways to make a 4 of a kind hand out of 5 cards, you can think of this as being dealt 1 card, which is a queen. So what's a probability, or how many ways are there to get a queen out of a deck? That would be 1 out of 13, right? And then to be dealt another queen, and another queen, and another queen. And then you have to be dealt with 1 more card as something else. Okay? So you have this poker hand, 4 of a kind, 4 queens. So it'll be 1 of something, okay, 1 out of the 13 different cards, times, and you want all 4 of them. So you want all 4 queens. First you're dealt the queen, then you want all 4 queens, and then you have to be dealt 1 other card. So there's 48 cards left in the deck, and any one of those will work for a 4 of a kind in a hand. So this is going to be dealt any card. This is this portion. Suits don't matter. Suits don't matter in a 4 of a kind, and you need 4 of them to match. You're going to need all 4 queens, or 4 aces, or 4 twos, or 4 nines. And then you need to be dealt 1 of any of the other cards left over. So you can do that as 13C1, 4C4, which is 1, and 48C1, which is 48. Okay, so to be dealt 1 card, a specific kind of card, it'll be 1 out of 13. To be dealt all 4 cards out of the deck, there's only 1 way to do that, because order doesn't matter, and then you can be dealt 1 more. So it's 624 ways that you can be dealt a 4 of a kind for a 5-card poker hand. Okay, here's your Google form. Some of these are going to be kind of tricky, so you're going to do this one. Number 2, what's the probability of being dealt a 5-card poker hand? That is a 4 of a kind. And you're going to answer this one. This is problem 36 on page 622. If you have a little bit of trouble with this, look at problem number 35, the one right before it, the odd number, and you have to answer in the back of your book. You want to try that one. You need to try this one, 38, payroll error. And number 37 is similar to this one. You may want to try that one and look in the back of the book for the odd answer. And then this one, and there's no matching one on this one in your book, so you need to do this one. Alright, that's it.